recording. All right. So here we are. Brave New World. So I posted these chapter 8 notes, but then I managed to only rename the file and not anything in it. It used to be chapter 5, now it's chapter 8. So if you go and make sure that you grab those off Moodle, where was it here? Dun, 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 dun. Oh, so many changes on Moodle. Anyways, tried to kind of update this week at least. Yeah, last week. Oh yeah, we got to talk about Lab 8. And okay, so it's the chapter 8 notes that you'll want to download and have, because those are the ones that we're going to go through, even though it says chapter 5 on here. Okay, first things first, Lab 8, can't remember when I said it was due, let me check, is not due until, I think I just made it due at the end of the term. I guess I didn't really say. Log me out. Okay, I'll have to double check. But I think due April 10th. If it's not, I'll change it to April 10th. How about? So what I'm going to do is I'm going to use your 7 highest lab grades. So if you missed a lab or whatever, then you can do Lab 8 to boost your numbers, right? And if you are good with your grade as it is with the 7 that you've done, then you don't have to do Lab 8. So I will use your 7 highest lab grades. So use Lab 8 to boost your marks if you want to. Oh yeah, assignment 8, mysteriously, because we fell behind, had already closed, but I opened it up because we hadn't even started the material for it. So assignment number 8 is due, oh shoot, now I'm still logged out here. Come on. Oop. Oh, here's the Lab 8. Yeah, April 10th, good. And let's see here. Assignment 8 is due on Monday, March 30th. Due March 30th, and it will be on chapter 8, which we're just starting now. So that's why I bumped it forward. Yeah. Oh man, so much housekeeping. Is that also the case for the, let me see here. It's not the case for the assignments. Let's see here. But oh, I do have a booster assignment for you guys. So I guess, should I talk about that now? Yeah. So thank you, Ruben. Not really. how about, I'll put it in writing here. No, but there will be a booster assignment. So the booster assignment is going to be later, but I'll just let you guys know about it. So what we're going to be doing for future tests, right? We've got the lab exam, which we're trying to figure out how to do, and also the final exam, of course. And so what we want to do is use a thing called grade scope. And so we'll do so the booster assignment is going to be just a practice upload to grade scope. Okay, so details later because we haven't set it up yet. Once your tests are marked, you'll get an email from Gradescope. Okay, so test 2 marks and feedback will be sent via Gradescope to your MyOkanagan email. Oops, didn't like MyOkanagan. Okanagan email. Okay. So you will get an email once that's done, and then it'll say something like, oh, check out your grades here. And then it'll have all your grades and feedback so that you'll have it to study from. Okay. What else are they going to talk about? Oh, okay. Your new grade breakdown. That was another thing. Probably should have grabbed a fresh piece of paper here. Oh well, we're too far gone. So the new grade breakdown. Your lab is still going to be 15%. I don't think that changed. I don't remember that changing. The lab exam, it might have been bumped a little bit. The lab exam is still 10%. Your assignments are 15%. Here's kind of the major change. Well, not really for the tests. The tests are 40%. And the final is going to be 20% instead. Okay. I cannot remember. What can I remember? Not much. Oh yeah, so the lab was boosted by 5%, and the assignments were boosted by 5%. And then we'll just do, so what I want to do, because it is kind of vague, the tests here, I'll just do kind of whatever weighting that benefits you. Right? And so now, this is why we're so glad that we wrote that test, so we have a test to kind of play around with. And then the final will be 20%. Okay, so it'll just be, we're just finalizing how to do that exactly, but it'll just be online. There's no more talk of face-to-face finals as far as I know, so we're just going to go ahead and figure out how to do it online. Okay. Dun, dun, dun. Good. Okay. Any questions? Please put them in the chat box, I guess, because that one seems to pop up. All right. So last day we talked about, well, we had our test last day, but the day before that, we finished talking about hypothesis testing for one sample mean sigma known. And so now we're going to start talking about one sample mean sigma unknown. Okay. Is kind of what we're starting to talk about now. So for the rest of the term, we're just going to start talking about different types of questions. And so far, we've only seen that one type of question, or at least for confidence intervals and hypothesis testing. And so now, what's going to be really important is that we try to figure out what type of question we have, so that then, once we figure out the type, then we'll know exactly what to do for each scenario. So, we already talked about, and we had a look at, if you've got your Z table and your T table in front of you, maybe, let's see here. So here's my Z table, clean it up, these are all old. Da-da-da-da-da. Here's my T table, right? And check it out, Notability has this new fun pointer action. Neat. I do have to kind of click back and forth. So anyways, so here's our T table. So what's different about the T table is that we've only used the Z star, right? And so we've only used this Z star row, and we've ignored everything else except for the top row, which has the confidence level, right? So we were able to use this to build confidence intervals. Okay. In between here, there's what we call the degrees of freedom, right? So here we've got the degrees of freedom. So that's what we need to establish now, what they do and what they're doing. And then if you'll have a look at the bottom here, we've got the one-sided P and the two-sided P, which sounds familiar because they are. These are going to be your P values. Okay. So how we find our P values is going to be slightly different. Okay. In fact, I would argue it's easier. Okay. But let's take a step back and just figure out what the difference between the Z and the T distribution are. And so we already had a look at, oops, the Z scores. Right, so we've got, so this is the Z that we've been using so far. We've got some sample mean X bar, right? Some hypothesized mean. Mu naught. The population standard deviation sigma. And then, of course, our sample size n. Everything else stays the same, except for with the T, right? The only thing that changed here, X bar stayed the same, mu naught is still your hypothesized mean, n is still your sample size, but S is your sample standard deviation. Okay. So here, right, notice that the only difference is whether we know sigma or not, right? So if we don't know sigma, sigma is the population standard deviation. So if we don't know that, then what do? Well, we can calculate the sample standard deviation and use that, right? And so here, this is going to be the important kind of distinction between the two. Wait, that's a huge marker. How about that? Oh, not big enough. I'll just do this here. Okay. So far, our questions, we have had sigma known, right? And so if our question has a sigma known problem, then we have, so something follows a normal distribution with a mean of this, and a standard deviation of blank, right? Or even assume the standard deviation for all, whatever we're talking about is this, right? And so now we're saying, okay, we know the population standard deviation, here it is. Okay? But we said in class a couple of times that that's not actually how things work, right? Because if you think about, well, what would it mean to have the population standard deviation? It means that you've collected your whole population and calculated the standard deviation, and then you threw them all back in the pond if you're talking about fish, for example, right? And that doesn't make sense. So more likely, right, in real life, this is what's going to happen, right? So real life, we never know sigma. Okay. So it becomes less choppy, right? Because then, so in a sigma unknown type of problem, it'll say, so you took a sample and you found the mean to be this and the standard deviation to be just something else, right? So from a sample, so you took a sample and you found the mean and the standard deviation. Okay. And so here, I guess I've got this note. Look at this. Put everything in here. So we'll never know sigma. And so what we're going to do is we're going to start calling these t-tests, right? So the difference between a z-test and a t-test. Okay. So what this says is that we will use t-tests as a default from now on. Okay. So unless it's obvious to you that you should be using Z, right? If you're not clear, then you should use a t-test. Okay. So the t-distribution is a little bit different from the Z because we've got this uncertainty in our sample standard deviation, right? It came from the sample. We don't know how good our sample is or how representative it is. So we have a couple of assumptions that we're working with. Okay. And so, well, our sample size has to be large enough, right? So n must be kind of greater than 20 to be able to do it. We'll still do it, but you should be checking for large enough samples. Of course, you have to have a random sample. And if the population has a normal distribution, then that's great, right? But otherwise, we've got the central limit theorem, right? So we can sample from non-normal distributions and the mean, or the distribution of the mean, the sampling distribution of the mean, the sampling distribution of the mean will approach a normal distribution for large enough n. Right, so n greater than 30, for example. And that's what we talked about at the beginning of chapter 7, where we talked about the central limit theorem and how cool it is that we can actually sample from non-normal distributions and still arrive at a normal distribution for the mean. And so here, what we're saying here kind of feeds into these notes here. So a large sample would ensure that the sampling distribution of the mean is nearly normal, and the estimate of the standard error as S over root n is reliable, right? And so before, we were saying that the standard error was sigma over root n, but now our standard error is going to be S over root n if sigma is unknown. Okay. So let's just kind of go through these little t-distribution facts and what changes and what stays the same. So the t-distribution is always centered at 0. So just like Z, it's centered at 0. So we can even put that on here. Right, centered on 0. So if you kind of zoom in, whee, the normal distribution is the dotted line. Notice how it goes closer to the curve and kind of approaches the curve quicker, or the axis quicker. So it kind of flattens down and it's on the axis pretty quick here, right? And we know from the 6895-99.7 rule that it's, you know, once you get to 3 standard deviations beyond the mean, then we're pretty well on the axes here. These axes never close, even for a normal distribution, right? But notice for the t-distribution, they leave a lot more room in the tails. If you remember, so if we kind of go a little outside the box here, the area under the tails, right? So if I kind of draw a little area under the tail here, area under the curve, I should say, right? This area is a probability. Oops, too thick. This is a probability. So what it means to have this more area in the tail is that it's just making room for a higher probability of more extreme values, right? So more area in the tail gives a slightly higher probability to more extreme values. To more extreme values. Okay. But otherwise, okay, so let's go back to, so that's what's going on in the tails. And in fact, if you go down to the next image that I've given you, okay, the t-distribution actually changes shape depending on our sample size. So let's talk about that first. So we said, okay, well, it has this bell shape. We know that. And the tails are thicker than the normal models. So we also talked about that. And so we said that observations are more likely to fall beyond 2 standard deviations from the mean than under the normal distribution, right? Because that's what we see here when there's more room in the tails. Not a lot more likely, right? You can still use ±2 as a cutoff, but it depends on your sample size. So these extra thick tails are helpful for if we have a small sample size, then we have more area in the tail. So small sample sizes have more area in the tails. And that's because we don't know, nothing's stable at small sample sizes, right? And so we need to make that room because we don't actually know how good or how bad our sample is. And so what we need is some way to communicate, wait, what happened here? Our sample size. And so the degrees of freedom do that. And so degrees of freedom communicate our sample size, right? So the degrees of freedom is just how we talk about our sample size. So you're going to have a t-distribution, and the t-distribution changes depending on the sample size. So what we've got here is we've got the normal distribution up top, and then the next one down is 10 degrees of freedom. They look very similar, right? So what's probably on the next page, yeah, is that the degrees of freedom, let's see here, is n minus 1. So it's your sample size minus 1. In fact, I'll put it on here. Our df, degrees of freedom, is n minus 1. So it's your sample size minus 1. So here, already at an n of 11, right, that would give us a 10 degrees of freedom. Our curve basically looks the same as a normal curve, right? So it's only for these very small sample sizes that it matters. Very small n. Then we've got this thick tail here, but for even a sample size of 11, the t-distribution starts to look like the z-distribution. Okay. So what we've got, if we have a look at our t-table, here is on the side, you've got your degrees of freedom, right? And so what we do is we figure out what our degrees of freedom are. And unlike the Z table where we can use anything in here in the body of the table, we actually, once you've decided that you have 15 degrees of freedom, for example, then this is the only line that you can stay on, right? You can't jump around. You have to use your 15 degrees of freedom, right? If you've decided. So that means you have a sample size of 16, right, to get 15 degrees of freedom. And so already you can probably tell, okay, well, how would I want, if I had to build a confidence interval, which we're not going to do quite yet, but if I had to, right, if I want a 95% confidence interval, it looks like my T star for 15 degrees of freedom is going to be 2.131. So we already know how to use this table. I'm getting ahead of myself, but we already know how to use this table. It's just for finding the p-values that's going to be different. Okay? But we already said that they're down here, so even that you can probably just kind of decipher. Okay? So let's talk about it. So using the t-table to find p-values, right, is, and I've got a bunch of blah, 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 blah. Here are just some good things to keep in mind. We'll come back to this. Wait. Guess it needs to be a little bit thicker. Highlighter. Okay, we'll come back to those. But I've put those there for a reason. Those are things that people kind of forget about, okay, when they're doing these problems. So we'll come back to those. So if you're using your t-table, right, then you're probably doing a hypothesis test, which means you've set up your null and alternative hypotheses, and we'll do an example so that you'll see. But it works the same way that it does for, as it did before, for one sample mean sigma known. So step one of hypothesis testing is always the same. Then in step two, when you do the test, you're going to calculate a t-score instead of a z-score. And then once you have a t, you have to use the t-table. And so here, one thing that you should notice is that there are only positive values in the t-table, right? And so what you do if you're using the t-table, right, and you have a negative t, then you have to use the absolute value. And just in case you've forgotten what the absolute value is, even though I think we've used it before, you had to use it on the assignment, on an assignment, right? But the absolute value of x is just the, you basically drop the negative, right? And so if you have a negative number, you take the negative of it, and that makes it positive. And so the absolute value, just drop the negative. Okay. So first thing you're going to do to use the t-table, so this is after you've calculated your t-score, you're going to first calculate your degrees of freedom. Okay? For one sample, the degrees of freedom is n-1. Just as a heads up, let's go to your formula sheet, right? And oh, I can remove these because that was for before. So here, right, for one sample mean sigma unknown, it gives us our degrees of freedom. Okay. Later on, right, we're going to talk about two sample means. We calculate our degrees of freedom a little bit differently, but we'll get there in 2 days from now. And again, so we've got degrees of freedom is n-1, degrees of freedom is n-1, degrees of freedom is the smallest of n1 minus 1 and n2 minus 1. So depending on the situation or the type of problem that we have, right? So I would call this our first type, our second type, our third type, and our fourth type, right? Just for now. So today we're working on our second type of problem. Next day we'll work on our third type of problem, and then the following day we'll work on our fourth type of problem. And then we'll just keep going and going and going, right? But regardless, it'll tell us what to use for your degrees of freedom. So that's not something that you have to memorize. I mean, now you're just working at home anyways, so memorize what? But so you have to find your degrees of freedom. That's the first thing. Okay. And then in the left-hand column, you're going to find your degrees of freedom. Okay. So this is of your t-table. So you have to find your degrees of freedom. And then what's important is that you can't stray from this row, right? So once you have your degrees of freedom, you can't jump around. That's the row that you're on, and you have to ignore the rest of the table. Then what you do is you move along that row to figure out where your calculated t that you've calculated, of course, obviously, that you've calculated would fall. Okay, so it's going to be between two values, most likely. Okay. So once you found the two values that surround your calculated t, you should record them like this. And once we do an example, of course, it'll look nicer. But what you'll see is all these problems, especially if we're calculating t's, which if you go to your formula sheet, right, here I'm calculating a t, here I'm calculating a t, and even though this looks big and nasty, I'm still calculating a t. So regardless of how you got that t, all the t's behave the same. So you'll start to see the pattern, and you can just apply that same pattern over and over and over again. So you're going to have two values. So now, and you know me, I like to kind of have my fingers on the table and just kind of boop, boop, boop my way around. So you should now have your fingers on the two t-scores that wrap around your calculated t. Right? Now you're going to follow these two values down to the bottom of the table. Right? And so And then remember how to decide if you have a one-sided or a two-sided test. That's in your alternative hypothesis, right? So from your alternative hypothesis, you will know if you have a one-sided or a two-sided test. Okay. Once you're at the bottom of the page, let me take you there. So let's say my calculated t is 2 exactly, right? Then I've got one finger on this guy and one finger on this guy, assuming I still have 15 degrees of freedom, right? And then I'm just tracing these down, right? Because 2, t equals 2 would be somewhere in here, right? Between 1.753 and 2.131. So what I do is I trace all the way down, and then depending on if I have a one-sided or a two-sided test, then I'm going to pick whichever row is appropriate. Okay. So notice, right, that these are decreasing as you move out further into the tails. Okay. So what's going on here is if you have a look at this guy, maybe I'll put him down here. Right. What this is saying, centered on 0 still, is that a t of 1.753, so that's the first one that we said, 1.753 has a one-sided p-value of 0.05. What it's saying for 2.131 is that it's saying, okay, here, let me zoom in so I can, 2.131 has a one-sided p-value of 0.025. What we're saying is that, well, our t that we calculated is somewhere here at 2. So all we can say is that the p-value, the one-sided p-value is somewhere between 0.025 and 0.05. So that's what it means when it says, okay, you read them from right to left, which I know is a little bit backwards, but it's because they're decreasing as we move out. So I'm just going to copy this into our notes here. So, don't worry, we will do an example and maybe even 2. We'll see. Okay. So now that's step 9 of using this thing. And so you record the p-values that you found, and that's what we did here. I guess I can try to zoom, make this bigger. Whee! It's hard. What's important and what kind of trips people up is that you can still compare the range of the p-value to an alpha level, right? And so just like we did before, even though you don't have a specific number, you know that the p-value is larger than 0.025 and less than 0.05. And so knowing that, if I asked you, okay, well, is it less than 0.05, which is our default, right? Default alpha level, yes, it is, because that's what my range is telling me. Right, and so this is less than 0.05. So our p-value is small enough, which means we would reject the null hypothesis here. Right, and so we can still use the range for the p-values. It just doesn't feel as concrete, but we can do it. Okay. Just going on to how to use the t-table, right? What you're going to do, and we already talked about this, right? We already kind of figured it out when we saw the table. So if you have to find a critical value, right, which is the t star for a confidence interval, right? And even if you go to your formula sheet, then it looks like if I want a confidence interval, then it looks like I need to use a T star instead of a Z star. So we know how to find the Z star, and we find the T star in the same way, except we have to use the degrees of freedom. And so same idea, right? You're going to find the confidence level that you want in the top row of the t-table. You're going to find your degrees of freedom, and then the critical value, right, is where the degrees of freedom row intersects with the column for the desired confidence interval. Okay, so I've got more of a summary here, but I would actually like to, let's see what time it is. Let's see here. Oh, sorry, Anna. I just saw your text from earlier. Can you hear me now? Sorry, it was like 30 minutes ago. Can everyone hear me? Or can anyone not hear me? How about we start there? That would be bad, wouldn't it? Oh, it's a chat here. Oh, sorry, Anna. Okay. Looks like my mic is it's on. Are you still having troubles? Let's see. Okay, awesome. So Brie can hear me. That's good. Good. Okay. Let me know if you didn't get that sorted out, Anna, but it sounds like, haha, pun intended. Sounds like we're all good still. Okay. Good. Otherwise, I'm just blabbing on my own here. Which can happen, I guess. It's okay. All right. So just to do a quick run through before we do an example, right? Just to show you that not a lot has changed, right? And so for your steps, for your hypothesis testing, your first step is still going to be to state your hypotheses. And in fact, it's still going to be, right? We still want to compare our sample mean x bar to a hypothesized mean or just a value. Sometimes it'll just look like a value. It is technically a mean, but it might be confusing if we have to look for a mean. But so to a hypothesized mean or value, U naught. Okay. And then, so the sign here is what tells us if we have a one-sided or a two-sided test, right? Because that's how we're going to pick our one-sided or two-sided p-values. Then in step 2, we're going to do the test, right? Which is where we calculate our t. Then in step 3, right, we use our t-table. So use the t-table with our degrees of freedom to find our p-value. And then our conclusion stays the same, right? So we use the p-value the same way throughout the rest of the course. In fact, all p-values behave the same. If you have a small p-value, so if the p-value is less than the alpha level, then what you're going to say is you have enough evidence to reject H naught. And then if you're rejecting it, then you may as well say in favor of what? In favor of the alternative hypothesis. If the p-value is not less than the alpha level, then you essentially just negate that sentence, right? So we do not have enough evidence to reject H naught. Okay. If you're not rejecting it, then you don't have to tell me what you're rejecting it in favor of. Okay. Are we ready for an example? Finally? Okay. So I'm on page 5, and so we've got this example, and what I want to kind of highlight is, because I write a lot around the solution, right, to kind of guide your thinking, I guess. Everything that you need for a complete answer, right, is in these boxes. So for when you're working on your own problems, as long as you've got everything that's in the boxes showing, then you've got a complete answer. Okay, so here's our example. The level of dissolved oxygen, DO, in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. Okay. And then we're told that the mean and the standard deviation of this sample are X bar is 4.771 and S is 0.9396. Okay. This is both from the sample. So X bar is always from the sample, and S and standard deviation. Oops, you know what? I'm not even going to mention the X bar because it's redundant. Standard deviation is from the sample. Oops. Therefore, sigma is unknown. Okay. And then this arrow doesn't really make sense anymore. There we go. Okay. So the standard deviation is from the sample, right? And so now that's how we know that we have a sigma unknown type of problem. Okay. That's your only guide. Otherwise, the problem looks exactly the same. So then the end of the problem says a dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. Is there evidence that the aquatic life is at risk at the alpha equals 0.05 level? Okay. So we're going to start off and do, so is there evidence that something usually means we have to do a hypothesis test, right? So is there evidence? This means that we're doing a hypothesis test. So that's where we'll start. Okay. Here, what's important is that we want to know below 5. Okay. So if the mean level, which is 4.771, right? This is our mean. That is less than 5, right? There's no denying that, right? But is it significantly less than 5, right? And so what we're doing here is we're asking, is 4.771 significantly less than 5, right? That's what we're asking. Okay. So what we want to do is start our hypothesis test. So step 1 is we have to state our null and alternative hypothesis, right? And so the value that I want to compare my sample mean to, right, is the 4.77, oh, sorry, is the 5, right? And so that's the value that I have to use here. Okay. So your null hypothesis is going to be that mu is 5, right? It's not significantly different from 5, it's just equal to 5. And then what we're interested in is if mu is below 5, right? Is mu less than 5? Because I'm only concerned with one side, right? This makes it a one-sided test, right? Which translates to later in step 3 when we have to find our p-value that we need a one-sided p-value. Oops, p-value later. Okay, so that's where that comes from later. And you'll see all around here, I've kind of talked around everything. Okay. But everything that you need to put is in the gray boxes. So that's step one. So we've got our null and alternative hypotheses, right? Keeping in mind that whatever you have here, they have to be the same. Whatever you have here, those have to be the same. We always have an equal sign in the null hypothesis, and then the sign in the alternative hypothesis will depend on the question. And also notice that these are statements, right? Okay. So step two, do the test. Doing the test means calculating the z-score before, and now it means calculating the t-score. It's about the same, right? And so we can calculate our t, and for t-scores are rounded to 3 decimal places. Okay, why is that? If you have a look at your table, so if you go to your t-table, right, these values in here in the body of the table, I guess I can use my pointer. These values are all t values. Notice that they all have 3 decimal places. So that's just to match the t-table. Right. So t-scores are rounded to 3 decimal places. Oops. To match the t-table. And so you're always rounding to match whatever table you want to use. Okay. So here, I get a t when I round it, I get a t of negative 0.944. Okay. So that's the t that I'm going to be using. Okay. In step 3, we have to find our p-value. So first thing we have to do is we have to take the absolute value, right? And so now this means that t, or the absolute value of t, I'll say, is 0.944. So I drop the negative essentially. And we need to know our degrees of freedom. So our degrees of freedom, and you have to show me where you work it out. Okay. You can just incorporate in your blurb. Okay. So this is the blurb that you'll always use. Okay. Same kind of setup. I'll highlight the things that could change, right? That will change depending on your problem. Degrees of freedom. For our case, right, we've got a sample size of 15, and so we've got 14 degrees of freedom. And then what we find is this is our calculated t. Okay. So if we go to our t table with 14 degrees of freedom, now this is not what we're working on anymore. Just to kind of clean up a little bit here. Even this, yep. Delete. Haha, nice and clean. Okay. So we've got 14 degrees of freedom. So here we are at 14 degrees of freedom. And what I'm going to do is I'm just going to draw a line and say, okay, these are the only values that I can look at. Okay. For 14 degrees of freedom, what I do is I try to, place my calculated t, right, the absolute value, so the 0.944, okay, try to figure out what values it would fall between. So if I go to my my table, I have 0.692, 0.868, 1.076. And so here, my 0.944 would fall somewhere in between 0.868 and 1.076. So I write those down as part of my work. Okay. And this is where you can recoup a lot of part marks if you pick the wrong interval, right? If you tell me that your t is somewhere between two values that it's not, then at least if you follow through to the next step, then you're safe, right? I'll have to dock you marks here for not doing that right, but at least I can follow through and make sure that you're doing it right. So we've got your calculated t, 0.944, is between 0.868 and 1.076. And then usually you can just say, which means that the one-sided p-value, right? Because you want to highlight that you know that you need a one-sided p-value, and that's from your alternative hypothesis up here, right? And so here we said we have a one-sided p-value because I'm only concerned with one extreme. Right? So then our one-sided p-value is somewhere between 0.15 and 0.20. So how we got there, if you go to your t-table again. So you've got your, kind of highlight these. You've got one finger here and one finger here. Then what you do, you know you need a one-sided p-value. So what you do is you trace down your one-sided p-value is between 0.15, right? So this is your first one, and 0.20, right? Because it's decreasing as we move this way, right? Our one-sided p-value is going to be between, it's going to be greater than, 0.15 and less than 0.20, right? And so this one went on this side and this one went on this side. So you have to read them in reverse, right? But that's only because of how the interval works, right? You have to list them from smallest to largest, assuming that you've turned your inequalities this way. Now, I always put my inequalities the same way. Notice here, right? My inequalities are the same. So as long as I change the order here and here, then I can just use the same setup all the time. Okay? And so I do recommend that you do that, at least until you're more kind of comfortable with inequalities, maybe. Okay? But until then, or even if you never feel comfortable with inequalities, that's okay too. Then just use this setup that I've got set up for you. Right, so this whole box goes as part of your kind of memory bank from now on. Right, that's how we're going to answer all our questions. So if our p-value is between 0.15 and 0.20, in step 4 for our conclusion, right, we want to compare it to, and it said the alpha level of 0.05, but I mean, that's the default, right? So it didn't even have to say 0.05, but it's just being explicit. So our one-sided p-values between 0.15 and 0.20, both of those values are larger than 0.05, right? So what we say is that since our one-sided p-value is between 0.15 and 0.20, here I'm just highlighting that I know what I found from here. Right, so from this third step in the fourth step, it's greater than our alpha of 0.05, okay, significance level, which means we do not, and I'll highlight that, we do not have enough evidence to reject H0. Therefore, right, so kind of, remember we have 3 parts of the conclusion. You want to compare your p-value to the alpha level. And then what does that mean in terms of your null hypothesis? And then your conclusion in terms of the problem. So if we don't have enough evidence to reject H0, right, then that means that we don't have enough evidence to conclude that the mean dissolved oxygen level in the stream is less than 5 milligrams per liter. Fish rejoice, woohoo! So, right, because that's a good thing, because remember at the beginning, it said a dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. So we were able to confirm that even though 4.771 is less than 5, it's not significantly less than 5, right? Because we were not able to reject our null hypothesis, right? And so that's a good thing for these fish. So good, 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 good. Oh, I guess I should say my notes, I obviously just stole them from another term. You can ignore the R code, right? R is instead of Excel, or, well, it's a little bit more sophisticated than Excel, but here's how you would do it if you had to use R. But all along the side here, I've just shown you how to use R if you wanted to, but we are not using R, we're using Excel. And so even things like this, this is just R code. Right. So you can ignore it if you want to, or you can use it if you want to. You can download R in RStudio for free, but we're not doing that for you guys this term, so don't worry. You get to use Excel instead. All right, how are we doing for, oof. Let me see here. Okay. So there's another example, but just so I don't run out of time, I want to skip to the confidence interval, right? And then I'll post the solutions to the example after class if we don't have time to do it. But just so some things, right, that you want to do when you're doing this example is just figure out what type of question this is. Right? Is it one sample, or, yeah. Because that's what you're going to want to do for the rest of the term. One sample mean sigma known. I guess I shouldn't use A. Or is it one sample mean sigma unknown? Okay. Well, of course, because we're talking about one sample mean sigma unknown, that is what it'll be. But what's the reason, right? So if we just read it, we're not probably going to do it, but Summit Projects is a full service interactive agency that offers companies a variety of website services. Summit recently redesigned a client company's website and wants to show that sales have increased. Before the redesign, the average sales were $24.85. After the redesign, an analyst selects 58 sales records at random from the client's 2,000 access logs, and she finds a mean amount spent of $26.05 with a standard deviation of 1020. So here, this is the sample standard deviation. Is there evidence that the mean sales have increased since the redesign? Okay. So here, if it's a sample standard deviation, then it's sigma unknown, so you have to use a t-test. Okay, so for the confidence interval, again, nothing really changes. except we have to find our T star instead of our Z star. But now that we know our way a little bit around the t-table, and I think once you get used to using the t-table, you'll like using it a lot better than the z-table, so you'll probably want to just use the t-table all the time, but it'll take a little bit of time to get there. So we still need our degrees of freedom, right? And X bar is still the sample mean, right? And so here, this is still our margin of error. Oh, of course, Apple Pencil running low, margin of error, right? And S over root n is still our standard error. Nothing changes except because our standard deviation is from the sample, we have to use T star instead. Okay, so if we jump to this example here, business bankruptcies in Canada are monitored by the Office of the Superintendent of Bankruptcy Canada, OSB. Included in each report are the assets and liabilities the company declared at the time of the bankruptcy filing. A study is based on a random sample of 75 records, which means our sample size is 75 from the current year. The average debt, liabilities minus the assets is 92,172. So X bar is 92,172 with a standard deviation of 111,000. So S, right, because it's from the sample, is 111,538. We want to construct a 95% confidence interval for the average debt of these companies at the time of filing. Right. So we're given, so we already highlighted all this information. And if we have a look at our formula that we need to use, right, we've got X bar, we've got X bar, we've got S, we've got N. The only thing that's missing is our T star. So what we need, and you're always going to use the same blurb for confidence intervals. So using the t-table with 75 minus 1, so 74 degrees of freedom. Here's the pickle. If you go to your table and you try to find 74 degrees of freedom, right? So here you're tracing down 1, 2, 3, 4, going up by ones until I hit 30. Once I hit 30, I go up to 40, 50, 60, 60, 80, 100, and then 1,000, and then it jumps to Z star. So what we have, right, for 74, we're choosing between 60 and 80, essentially. Even though 74 is closer to 80, we still have to round down to 60. And I've got that note in here, but I kind of glossed over it until we needed it. But let me take you back there. Probably in using the t-table. Oh yeah, here, in the general things to keep in mind that I said we would come back to. But we've talked about all these things already. T has to have 3 decimal places. If the degrees of freedom aren't in your table, you must use the closest degrees of freedom rounding down. Remember, if you're rounding up to 80, for example, then you're saying that you have a sample size of 81 when you only have a sample size of 75. So that's bad. Right? And then, so if it happens that the t-score that you calculated is beyond the range of the table, right? That's either on the left side or the right side, then this is how you would phrase your p-value. So here's on the smaller end, here's on the upper end, but all those points are there. So when you need them. Okay. Where were we here? All right. So if we use, so then what you say, so you need 74 degrees of freedom, but you don't have it. So then you're saying, but using 60 degrees of freedom instead. So if we go to our table and we use 60 degrees of freedom here. Then, and I want a 95% confidence interval. Looks like I've got a perfect 2.000 T star. Right, so here 2.000, which shouldn't be that surprising, right? From the 6895 99.7 rule, right? We're expecting it to be around 2. Now it's exactly 2. So then we can go through and we can do our calculations. And so we've got 2.000, that's our T star. And then we calculate our margin of error here is 25,758 and basically 60 cents, right? Because now we're talking money, so we can round to 2 decimal places, but you don't want to round too soon. So just keep all your decimal places until the end. And then when you round it to money, then you can have 2 decimal places. Remember our blurb for our confidence interval before, right? So we're 95% confident that the interval from 66,413.40 cents to 117,930.60 cents captures the average debt of these companies at the time of filing, right? Because we wanted to make a confidence interval, construct a 95% confidence interval for the average debt of these companies at the time of filing. We just steal that little bit and tack it on at the end here. Yeah. All right. So again, there's another example, but what I'll do is I'll just make some room here. What I will do, where's that example? I'll scoot this. I wonder if I can I? No, not that. Copy, paste image. That might be good. And then I can delete this. Just to be able to make a new page. In here, so that I can put my work here. Add a page. So what I'll do is, before I'll post these notes, I'll do this example here. Example 2. We don't have time to do it now, today, but I'll just tell you guys where to find it. So here's example 2, or here's where you will find it when I post these notes. And I'll do the same thing for the next confidence interval one, which is a manufacturer of high-resolution video terminals must control the tension on the mesh of fine wires that lies behind the surface of the viewing screen. The tension is measured by an electrical device with output readings in millivolts. A random sample of 20 screens has a mean of 306 and a standard deviation of 36. Give a 90% confidence interval for the true mean tension mu for all the video terminals produced this day. So here, first thing you want to do, right, is figure out what type of question it is. Convince yourself that this standard deviation came from the sample, right? And because it says a random sample of 20 screens has a mean of 306 and a standard deviation of 36, right? That's what makes this standard deviation from the sample. So one sample mean, sigma unknown, because of that, right? A random sample of 20 screens. And the standard deviation came from the sample. SD is from the sample. Okay. So I'll make another page here, just in case I need it. And that's where I'll put example 4. Okay. All right. Let me go back here. Any questions? Nobody? I don't know how to know if you don't have any questions. Anyways, that's all we're doing today. Thanks for watching. Be sure to like, subscribe, comment below, all that fun stuff. Anyways, I guess I'll see you guys, well, not really see you guys, on, oh, hey Manuel.
Hi.
Bye guys. Got a little bit of overlap here. On to the next one.
Yeah, okay.
All right, bye guys.
Bye-bye.
So funny. Okay, I gotta end this recording here. Stop. Okay. I'll be back, Manuel. I'll be back.
Yeah, sure.
You might. It might boot you out because I'm gonna end this meeting so that the recording stops, and then I'll be right back.
Okay. Okay, no problem.
Okay, bye.